On the night of November 23rd, 1601, the chambers of the imperial mathematician of the Holy Roman Emperor were filled with the agonized pleas of a man. Let me not seem to have lived in vain. This man, noble of birth, was dying. 11 days earlier, he had attended a banquet held in honor of Rudolf II, by some accounts the most powerful man in Germany, by others an emperor not entirely in possession of his mental faculties. A peculiar man, Rudolf was given over to bouts of melancholy that seemed to find more comfort in the various workings of the machines and contraptions he kept in the palace. On the night of the feast, the emperor had resolved to drink only sparingly, for toasts and the like, in order to remain alert and attentive to the affairs of state. Unfortunately, for the guests at the head table, he had kept this to himself, and so they indulged, as was their usual custom, enjoying the bounty of a larder stocked from all over Europe. For most, consumption of the delights of the table were restrained by moderation, and a caution born of knowing the strange moods of their ruler. Not so for the new nobleman, brought to court just a year earlier. He imbibed freely, and with the gusto he was known for. He was a grand, vivacious man, a bon vivant, who through his familiarity with power and royalty was as comfortable as any at the head table. He drank, and in time, he felt the inevitable call to relieve himself. Unfortunately, it was at this point that physical necessity encountered an even more imperative reality, that of social custom. In Prague, at the court of the emperor, it was considered a dire breach of protocol to excuse oneself from the table before His Eminence had. As the discomfort grew, Rudolf, sipping only occasionally his glass, engaged courtier after petitioner in conversation. Soon, the nobleman was in a state somewhere between drunken numbness and blinding agony, at least until something shifted. Finally, near the end of the evening, the emperor took his leave of his guests, and the nobleman staggered to the private chamber, only to find that he could not urinate. Within a day or two, it became apparent that something was seriously wrong. He could only pass very small amounts of urine and had begun to run a fever. Over that next 11 days, his condition worsened until on this night it was clear to all that the end was near. Let me not seem to have lived in vain. Earlier in the week, as it had become more and more apparent that there was nothing the physicians could do, the nobleman had called his most talented and brilliant assistant and charged him with completing his table. They were to have been his greatest work in a life filled with great work. Constructed from his model of the cosmos, they were based on the most precise data that had ever been gathered by any scientist, living or dead. Now he stood on the threshold of that final transition, and, lingering there in his delirium, he questioned whether all he had done really mattered. Let me not seem to have lived in vain. As the assistant and an attending physician kept watch, the nobleman's condition worsened, and his voice became more feeble. The man whose personality had once been big enough to fill an observatory and, indeed, an entire island, now shrank into himself with fevered mumbling. Let me not seem to have lived in vain. In the early morning hours, his breathing grew ragged, and then, as all knew it would, it stopped. So ended the life of Tycho Brahe, killed by sepsis brought about by a ruptured bladder. For a generation he had been the greatest observational astronomer in human history. Now, as his suffering passed and his body grew cold, his legacy would have to be carried on by a man who greatly respected his vast contributions, but did not share his views of the structure of the universe.
Hello, and welcome to the Scientific Odyssey. The Scientific Odyssey is a many-part journey into the history and philosophy of science. My name is Chad Davies, and I'm the writer, host, and producer of the podcast, where we consider the ideas, processes, and results of over 2,500 years of scientific inquiry and discovery.
Series 3, Finding Our Place. Episode 15, The Tychonic Model. This week, we're going to take a look at one of the most interesting and vexing figures in the history of astronomy, the Danish astronomer Tycho Brahe. As is our custom, we'll divide the discussions into two parts, one focusing on his scientific contributions with a supplemental biographical episode looking at the various aspects of his life and personality and how they interacted with and affected his work. Thus, in this episode, we'll only take a passing glance at the man whose observations of the heavens and their motions set the stage for the next part of the great and at the time almost invisible revolution that was taking place in Europe. Tycho was born on the 14th of December in 1546, 3 years after the publication of Copernicus's De Revolutionibus. He was of noble lineage, with connections to not only many of the most prestigious families of Denmark, but also to that of the king, whose family his had served for many generations on the Privy Council. Groomed to fill that role as he grew up, Tycho received a first-class education, beginning at a rather amazing age of 12 his studies at the University of Copenhagen in 1559. Throughout the 1560s, he would pursue a course of study that would prepare him to serve in the role his family had for centuries, but also included the full liberal arts curriculum, including astronomy. His interest in the subject was first piqued when, in 1560, he observed a solar eclipse that had been predicted ahead of time. While the prediction had been close to being correct, it was a day off, an indication that the tables of the time, whether derived from the mechanics of Ptolemy or Copernicus, were in need of some refinement. In 1563, while studying in Leipzig, he observed a conjunction of Jupiter and Saturn, a rare occurrence due to the slow motions of the two planets through the heavens. Here again, the planetary tables were somewhat inaccurate, and it seems to have been at this point that Brahe realized and recognized that the solution to these inaccuracies was to obtain better observations in order to be able to calculate better values for the various parameters in whatever model the astronomer might use to construct his or her planetary tables. It is at this point that the now young man begins to keep detailed observational records and seek out better observational instruments with which to observe. In 1566, while studying medicine and astrology at the University of Rostock, he became involved in a running dispute with another student over a variety of issues, including who was the more competent mathematician. In late December of that year, he and the other student decided to settle the matter with a sword duel. While Tycho may have been better with the work of astronomy, he was the poorer swordsman, and in the melee, lost his nose. For the rest of his life, he would wear a variety of prosthetic proboscises made of various materials. While contemporary accounts relate his having false noses made of gold and silver, modern forensic pathology conducted on his exhumed body indicates that, at least later in life, he tended to wear noses made of brass and adhered them to his face, made with plaster that he probably created himself. A year later, he returned home where everyone expected him to begin that life of an aristocrat closely allied with the king. Instead, Tycho seems to have looked around and decided that such things held little interest for him. Unlike Copernicus, who seems to have felt a bit trapped in the duty that awaited him, Brahe might have felt less bound to the traditional roles, especially as he had 8 siblings who could do the work instead of him. One other thing, given Brahe's later attitudes, something we'll discuss in detail in the biographical episode, he may have thought court life beneath his intellect. He was bright, meticulous, and filled with curiosity. The sorts of things he would do as an aristocrat amounted to, at least in his eyes, little more than accounting and some basic understanding of the law. Moreover, a lot of the people around him just weren't as bright and curious as he was, or at least that's how he saw it. What he wanted to do was continue his scientific work, especially in astronomy. Nevertheless, upon returning, he was appointed as canon at the cathedral in a place called Roskilde, a role similar to that played by Copernicus. In this case, however, it was understood that his filling the position was something a bit more ceremonial, so as to allow him time to continue his astronomical work. 3 years later, amidst some family turmoil, he was able to build an observatory and an alchemical laboratory at the Hevervad Abbey with the support of his uncle. At the end of that year, in 1571, Tycho would fall in love with a woman who was a commoner. Intelligent and inquisitive, Kirsten Hansen was the daughter of a local clergyman. Though forbidden by Danish law to formally wed, they were able to eventually find legal status for their marriage through something known as morganatic law, which said that if a nobleman and a commoner lived as husband and wife for 3 years, they were considered to be legally married. It would be during this period that Tycho would spot the new star in the constellation of Cassiopeia and begin his extensive observations of it. As we mentioned in the last episode, Tycho's establishment of the observational fact that the star did not display parallax argued very strongly for the position that it had to reside outside the sphere of the moon. This was a blow to the Aristotelian view that the heavens, the realm of the unchanging and eternal God, could not change. A position long endorsed by the scholastic tradition, by the way. His conclusions were published in 1573 in De Stella Nova, followed by a full set of observations in 1574. These two works established him as one of the, if not the most premier observational astronomers in all of Europe. In 1575, he went on a lecture tour to promote his ideas and act as something of an agent for the Danish king. It was pretty clear that the various academic institutions in Europe were very interested in snagging Tycho, but it was also clear that he was still in the service of his lord in Copenhagen, as he arranged for a number of Italian craftsmen to travel to the Danish capital to do work there. As the tour wound down towards its end, Brahe began to make secret arrangements to take a position at the university in Basel on the border of Switzerland, or at least what is now Switzerland. Recognizing that the astronomer would never accept the life of a courtier, King Frederick II of Denmark made Tycho an offer he couldn't refuse. He would give him the island of Hven in the Baltic Sea and fund the construction of an observatory there by allowing Tycho to collect rents from other lands in the realm. The young astronomer, seeing the chance to build something truly world-class, agreed to stay. He named the initial scientific facility there Uraniborg, or Castle of the Heavens. While it was being constructed, Tycho made his observations of the 1577 comet. As we've mentioned the comet observations in our last episode, there are just 2 additions I'd like to make. The first is in relation to an article I recently read. Ralph Neuhauser, Paul Kunzinks, and Rob Van Gent recently submitted a paper to the Journal of the History of Science that investigates the idea that Tycho may not have been the first person to suggest that a comet existed outside the sphere of Venus. Apparently, in support of his observations, Tycho referenced the work of a 9th century Islamic astronomer, Abu Mashar, who had claimed that he had evidence of comets existing above the spheres of air and fire. Mashar had come to this conclusion by observing a conjunction of Venus with a comet. He observed Venus's brightness as the comet approached it in the sky. When the planet and the comet's tail were together, i.e., in the same place, he reported that the brightness of the planet did not change. His thought was, had the comet passed between the planet and the observer, the planet should have become less bright. From this, Mashar concluded that the comet must pass further from the Earth than Venus did. Now, it turns out that this argument is actually incorrect, as the tails of comets are too diffuse to cause the expected decrease in brightness. But it is possible that Mashar's ideas may have helped Brahe accept the possibility that the comet was careening through the celestial realms. So why is this such a radical idea, or would it have been such a radical idea at the time? If you will recall, both Ptolemy and Copernicus had built a structured cosmos. Neither man could imagine the kind of universe we now take for granted, one in which rocky worlds hurtle through mostly empty space guided by some sort of invisible force, something we now call gravity. For them, and all other astronomers of the time, there had to be things up in the heavens to support the motions of the planets. One way to imagine this is to sort of think of an old mechanical clock that required intermeshing gears and engagements to connect the driving mechanism, say a pendulum and falling weights, to the motion of the various hands that told time. In the period before the middle of the 16th century, astronomers and natural philosophers could not imagine a universe where some kind of driving structure didn't carry the planets and stars through the heavens. Having a comet hurtling through that structure should have shattered it, especially if the etheric matter had been crystalline, as thought by many, or at least it would have disrupted the motion of the planets if that material were actually fluid. If Tycho had been committed to a structure-based picture, and there's no reason to imagine that he hadn't been up till this point, placing a comet that moved through the heavens fairly rapidly would seem like a contradiction. One way to resolve this would have been to say that the comet moved within a space allowed by the epicycles. However, when Michael Maestlin did his calculations as to the distances for the comet, that seemed pretty unlikely. As Sherlock Holmes was wont to say, whenever you eliminate the impossible, you must consider the improbable, however unlikely that might be. If the comet seemed to cross the places where there should be crystalline spheres, it might just be that there weren't actually any spheres. And this is, I think, one of those places. Another one of those revolutions in a single step sorts of things. Because while it doesn't necessarily mean that Ptolemy or Copernicus are wrong, it does eliminate a constraint we've just sort of implicitly assumed at this point. One of the things having a physical structure requires of any model is that the spheres can't actually cross each other. The path of one planet can't cross the path of another. In both models, geocentric and heliocentric, this rather logical assumption was required because you have these spheres that nest one inside of the other like Russian dolls. In fact, Ptolemy had used this assumption to create his full cosmological model that he had published in the Tetrabiblios. If there weren't any spheres, that meant that the structure can be given up. And if the structure can be given up, then the constraints on the arrangement of the planets also disappear. Now, if you want, planetary paths can cross each other. While it'll take a little while for Brahe to fully appreciate this and then to integrate it into his thinking, the change will have very important consequences for our story down the road a bit. As we look at the work of Tycho during this period, we need to spend a little time on Heaven and Uraniborg as institutions. In a sense, Uraniborg is a physical realization of the most fundamental aspect of Tycho's work, the almost overwhelming drive to get better observations in order to correct the models of the cosmos. Tycho was frustrated by the inability of both the Alphonsan and the Prutenic tables to make really accurate observations of planetary events, such as conjunctions and eclipses. They got close, but an astronomer worth his salt would use these as guidelines to develop what we might think of as observing windows. If the tables predicted an eclipse on a given day, say April 15th, an astronomer would sort of use this as the center of a window that might extend a month in either direction. While the observational fact that lunar eclipses only happened at full moons and solar eclipses at new moons would restrict the possible dates on either side of that predicted date, it was still a bit hit or miss. Brahe, like most other astronomers, felt that the problem was not so much in the models as it was in the parameters within the models, various values of variables that had to be inserted by hand, things like the rotation rates of various spheres. These values were determined by observation of the uneven rates of motion of the planets through the sky. If you had inaccurate or imprecise data from your observations, then you'd get inaccurate or imprecise values for the parameters. The problem was that there weren't any good observations except those that dated all the way back to the time of Ptolemy or earlier. Copernicus had made some observations, but he wasn't a great observer and he had pretty rudimentary equipment. Those from earlier times, men such as Ridio-Monte, were better observers, but their instruments were even cruder than those of Copernicus, and so their observations weren't very good either. Tycho, through his various youthful travels, began to work for two things. The first was just to make more careful observations. He soon recognized, however, that the limitations imposed by the instrumentation might be the actual bigger issue. His first notebook, devoted to systematic keeping of astronomical data, dates to 1563, maybe late 1562, while he was still traveling as a student. In that year, he observed that the Alphonsine tables missed a prediction of a conjunction between Jupiter and Saturn by almost a month, with the Copernican Prutenic tables doing a bit better. In 1564, he acquired his first real astronomical instrument, a cross staff. This was basically a staff about a meter in length that had a crosspiece that could be slid away from or towards the user as needed. The trick to using this was sort of to look down the staff and slide the crosspiece towards or away from the eye until two objects aligned with sights on either side of the crosspiece. Once this was done, the position of the crosspiece on the staff could be noted, and with the use of the table of tangents, such as the one Rheticus had produced, the angle could be determined. The instrument was a step up from what he already had, which basically amounted to a piece of string and a small globe, but Tycho soon found that it had some really significant limitations. While he was able to learn some workarounds and corrections and improve things somewhat, he began to think that there needed to be something done about the state of instrument making in astronomy. In 1569, once again while traveling as part of his education, he had a pair of compasses made for him while he stayed in the city of Augsburg. While we call them a pair of compasses as there are two moving pieces, one should understand that like with a pair of scissors, the compass needed both parts to perform its function, which was to measure the angle between two objects in the heavens. While this instrument was a marked improvement over his cross staff, it still fell short on two counts. The first was that he found it impossible to mount on some sort of stand, thus making it almost impossible to hold steady. Second, even if the stability problem could be solved, the scale that could measure the angle was not precise enough for Tycho. His goal was to get to the point where his instruments could measure the angle to a precision of 1 minute of angle arc. As you will recall, a minute of arc is 1/60th of a degree. Your finger, held at arm's length, is about half a degree or 30 minutes of arc. If you look at that, his goal here is a pretty big goal to try to achieve, and the instruments of the day were certainly not up to the task. Soon after this, with the backing of a wealthy patron, Tycho designed and had built what was the largest instrument he'd ever produce, a 20-foot tall quadrant. This is sort of like a giant protractor, but only having 90 degrees instead of 180, and it hung from a pivot. The pivot sort of thing was at the 90-degree vertex, and so the thing would hang with sort of the curved side straight down. Now along one side there would be a pair of sights, and the whole thing would be rotated up until a star could be seen through those sights. Now a plumb bob would be hung from that vertex, and where it crossed the arc of this protractor-like thing would be what would be used to determine the angle that was measured. And this would allow you to measure a star's elevation or altitude. And then the whole thing, the whole contraption here, could be rotated around so that the azimuth, or the angle around the horizon, could also be measured. If this were done for two objects, some spherical trigonometry could then be used to determine the separation of the two objects, say a planet and then some bright star, on any given night on the celestial sphere itself. All of these things would follow him back to Denmark and Heravad Abbey, where he set up his first observatory and made those observations of that new star for De Stella Nova. While at Heravad, Tycho, working with the local craftsmen, developed an instrument that worked with either a 30 or 60 degree arc, they were interchangeable, for measuring an angle by combining the functions of that pair of compasses and a quadrant. Tycho gave the instrument the name of the sextant, and it was a pretty impressive step forward in terms of astronomical measurement. In this project, though, he came to the conclusion that to get instruments of the precision he hoped to reach one day, he would need to employ the most skilled and talented of Europe's craftsmen, who would then work under his supervision. While the workers he had there at Heravad were certainly up to the day-to-day task of fabricating wheels for carts and that sort of thing, they fell a bit short for what Tycho was hoping to achieve. All of this fed into what he hoped to accomplish on Haven. Granted the necessary income and provenance to create what he had in mind, Uraniborg was designed to be the best astronomical and alchemical facility in the world. It would not only house the best instruments, but also have the necessary workshops to create whatever it needed to do its work, which included facilities for glassmaking, wood and metal fabrication, and even a paper mill and printing press, so that the observatory could publish its own work. Beyond this, however, it would have the ability to house and feed a number of craftsmen, scholars, students, and assistants. In short, Brahe set out to create the first fully functioning research facility or institute ever created in Europe. The last thing we know of that was this extensive may have actually been as far back as the Library of Alexandria, or maybe the House of Wisdom in Baghdad. It was a truly remarkable facility dedicated to getting the best observational data ever gathered and assembled. Now, there were a couple of broad research agendas that were initially pursued. The first was just creating a map of the sky. The last really good map/catalog was actually the one in The Alchemist. Creating a new catalog required each star to be measured with respect to several other stars and then related to a common starting point. These measurements had to be taken and then checked multiple times for what ended up being about 1,000 stars using several different instruments in order to eliminate the possibility of what we know as instrumental bias. Another project that he undertook was to get the measurements of the motions of the planets. Tycho wanted to get the 4 important measurements Copernicus had, but he also wanted to get a whole lot more. We'll talk a little bit about that in a bit. Given the slow motion of Jupiter and Saturn through the background stars, it would take a number of years to get full data sets for those 2 objects. Finally, Tycho wanted to see if he could detect stellar parallax, and this is where we're brought back to that original idea of the models. Tycho had an interesting relationship with the 2 models that were available to him when he came on the scene. Like Copernicus, he was contemptuous of Ptolemy's equant. In fact, he really admired Copernicus' decision to get rid of it and was impressed by the mathematical construction of the heliocentric model. The problem was that he was having a really hard time believing that the Earth moved. It just seemed like an idea that was just preposterous. As much of a maverick as Tycho could be, he wasn't ready to accept a moving Earth without some pretty strong evidence. For him, that evidence might have been found in what is known as stellar parallax. The idea for this is, if the Earth is revolving around the Sun like Copernicus said it was, then if a star is observed from 2 locations of the Earth's orbit 6 months apart, then the star's location with respect to the other stars around it should shift a little bit. The great thing about this research project is that it could be integrated into the Star Catalog project if the observations of the stars were made repeatedly throughout the course of the year. The problem was that the phenomenon of this shift was never actually observed. Even as Tycho's instruments got more and more precise, he never observed the stellar parallax Copernicus' model predicted. Now, a lot of the discussions of this I've seen said that from this data alone, Tycho concluded that the heliocentric model, no matter how useful it might be for calculation, was just physically wrong. Turns out, though, that the truth is a bit more complicated. Tycho recognized that there was a maximum distance out to which he could have detected parallax. So what he's actually shown is that either the heliocentric model was wrong, or, and this is a really important thing, or that the stars were a lot further away than previously thought, even by Copernicus himself. So why does Tycho go with this first conclusion? There are two reasons that I've been able to find, one theological and the other physical. The first is that if the stars are really as far away as the observations would suggest, that seemed like just a huge waste of space. And why would God have done that? Why would God have created a universe so full of nothing? The second had to do with another really clever, but ultimately flawed observation. As we've said, the sky moves at a pretty constant rate when observed from the Earth, about 1 degree of arc every 4 minutes of time. And we need to make sure, by the way, as we go forward here, we keep minutes of arc clearly distinguished from minutes of time. They're different things, even though we use the same word. What Tycho realized was that he could determine the angular size of a star by timing how long it took for the star to move behind something like the moon. To be more precise in my description here, he would sight on a star, and when the outside edge of the star's light touched the edge of the moon, he would start timing. He would stop timing at the instant the star completely disappeared behind the moon. And from this, he could sort of get a sense of how big the star actually was in terms of its angle. Now, this was an observation best done near the time of a crescent moon, where most of the disk of the moon is dark but ever so slightly illuminated. When he did this observation, he came up with an angular size for the star that he then used, along with that minimum distance the star had to be away so that he could observe no parallax, to calculate the size of the star. What he came up with was that stars would have to be at least as big as the Earth's orbit around the Sun. And this also just seemed to be preposterous. And so from that, Tycho rejects the heliocentric model. Now, before we dismiss our man here as being kind of dumb, I think it's pretty clear that he's using pretty good thinking. At this point, no one knew that there was what we would now call an aperture effect with the eye that made stars look bigger than they really were, something that wouldn't be discovered for about another 50 or 60 years. In addition, Tycho here is pushing the boundaries of observational precision, and so he's thinking that if anyone's going to be able to see this effect, it should be him. What he also doesn't know is that the naked eye just won't be able to observe or see stellar parallax because that quantity is just too small. It will require the use of a telescope to see the phenomena, and that wouldn't be invented, much less used for this purpose, for another 40 years. Brahe, in this sense, is really a man before his time, trying to do things that the human eye just can't do, no matter how great his tools were. So, for the next 20 years, Brahe would work on these research programs and would make instruments and observations on Heaven. He would add to Uraniborg a second facility called Stjerneborg, or Castle of the Stars, that would allow him to build larger and more precise instruments that would not be buffeted by the high winds that occasionally whipped the island, and allow two groups of research teams to take observations independently of each other so that those could then be compared to make sure there was no sort of collusion or bias. During this time, there would be one failed observing project that had to do with the planet of Mars. If the Ptolemaic model of the cosmos had been correct, Mars's distance from the Earth should have changed only a little bit and certainly less than that of the Sun. If Copernicus's model was correct, Mars' distance from the Earth would have changed a lot more than the Sun's. The idea Tycho had, a bit like an archer with only one arrow in his quiver, was again to use this idea of parallax. He wanted to measure the parallax of both Mars and the Sun and to see at different times of the year what they were and which was bigger. His initial attempts to do this were muddled and confusing until he realized that the Earth's own air would bend the light from the objects depending on those objects' angle above the horizon. He spent about 2 years getting a handle on this and then took additional measurements of Mars at the next available time of opposition. These indicated that Mars did come closer to the Earth than the Sun did, thus supporting the Copernican picture. However, as we have said, there was no other evidence that seemed to say that Copernicus was right. And so, that seemed to indicate that the Earth had to be stationary. So how was Brahe to resolve this? Well, there had been, since the time of the Greeks, models floating around every so often that had the Earth being stationary, with the Moon, Sun, Mars, Jupiter, and Saturn orbiting in it. However, in these models, Mercury and Venus were thought to orbit the Sun as a way to explain the maximum elongation observations that we've mentioned in the past. One of Brahe's assistants had brought this idea up with him, and he found it kind of intriguing. He asked himself, why not have more planets orbiting the Sun? The reason had been, before, that to do so would have required Mars and the other superior planets' orbits to cross other planetary orbits, something not allowed if the cosmos was constructed out of these crystalline spheres. And this is where, all of a sudden, the observations of the comet of 1577 become so tremendously important. Remember, these observations seem to indicate that there are no spheres. However the planets move through the heavens, they do so without being attached to any sort of structure. So if that's true, the constraint to Mars orbiting the Sun is now completely gone. What seems to be the case is that Tycho had been thinking about this sort of thing for a while, but the Mars parallax observations convince him that Ptolemy can't be right. So he works up a model, now known as the Tychonic Model, sometime around 1587. So what is this model specifically? In this model, there is a center of the cosmos from which the Earth is offset a bit, just like in Ptolemy. The Sun travels around this center on a circular path, though it's no longer actually, on a sphere. The same is true for the Moon. All of the other planets, however, now orbit the Sun. We'll post a link to an animation of this on the website, thescientificodyssey.typepad.com. What Tycho is able to do is show that he can get the same configurations of observational triangles for the planets that Copernicus does. And when he does this, he's actually able to use a good deal of Copernicus's math in his work afterwards. It's a pretty brilliant leap, and it seems to be supported by all the data he has at hand, at least at that time in about 1587. Unfortunately, in a later set of observations taken just a couple of years after this, he finds that his refraction tables for the Earth's atmosphere is just filled with errors. When he goes back to retake the data and recalculate things, he finds that the measurement of Mars's parallax completely goes away. Once again, as was the case with stellar parallax, Mars is just too far away to measure the parallax for just using the naked eye. Nevertheless, the model is still out there and is now considered a more than viable candidate. In fact, it won't be that long before it begins to supplant the Ptolemaic model in the eyes of many theologians and natural philosophers as the correct geocentric picture. In the eyes of many, the Tychonic model combines the best features of the Copernican model with the stationary Earth of Ptolemy, while disposing of the equant. While the model still requires circular paths, it does not have the physical structure of the spheres. And so one more small step in the revolution is taken. By this point, the reversal on the Mars parallax data was not the only setback Tycho was facing. One of his students had stolen data and drawings from his study and had then fled Havana only to show up in Germany with a version of quote-unquote his model, in other words, Tycho's model, than he had claimed to have come up with. This would embroil Tycho in a priority dispute that would drain his energies. Additionally, a number of family difficulties began to drag him down as well, as did a conflict that had arisen with the royal family of Denmark. On top of all of this, however, is that Brahe's personality seems to have undergone something of a change after about 1590. While he was not what one might call a model human being prior to this, he does seem to have been mostly kind and generous to those around him before that. One can even make a good argument that he went well beyond the social restrictions of his time to interact with people outside of his class and station, something we'll address in that next episode. After 1590, that seems to shift, or at least begin to. He becomes less attentive to detail, more paranoid, and a lot more vindictive. While it's hard to pin down the cause of this change, one has to wonder if the aristocratic lifestyle he had maintained on his island had begun to take its toll. Part of this was that he was now sort of the lord of his own little universe on the island, and had begun to see himself as an heir to more than his Danish heritage, but rather to the aristocracy of Western civilization and learning, if one can put it that way. He was more than a Brahe. He was treading in the footsteps of Plato and Aristotle, Ptolemy and Copernicus. Who else had developed a model of the cosmos? Who else had measured the heavens and inscribed them on the largest celestial globe in all of the world, something that sat in his study there at Uraniborg? Another contributing factor likely had to do with the probably rather large quantities of alcohol he consumed on the island. Tycho lived large and liked it. While not unusual among Danish aristocracy, most of his peers, subjected to the elements and engaged in warfare, rarely lived to the age that he did. It's not unlikely that some of the mistakes he made, especially after 1590, were due to the effects of a long and comfortable relationship with the bottle. Whatever the case, it's clear that by 1596, his reputation besmirched by an ongoing lawsuit with a suitor for the hand of one of his daughters, Tycho was deeply unhappy with things in Heaven. When a group of commoners, long unhappy with the demands he placed on them in his various fiefdoms, rioted outside of his home in Copenhagen while he was visiting there, he decided it was time to leave. Packing up some of his instruments, his notes and data, and his family, he left, never to return. For 2 years he floated around various places in Germany until he was offered a more permanent position in the court of the Holy Roman Emperor Rudolf II in 1599. Upon arriving, he built an observatory about 30 miles from Prague, which he ran for about a year before being called back to the court of the emperor. In Prague, he and his family were treated as nobility, and he fit in well, even as he feuded with another astronomer there, one Nicholas Reimers, more commonly known as Ursus or the Bear. The two argued over who had priority of the Tychonic Model, with Ursus claiming that he had come up with the idea on his own, because he had his own sort of version of it, and he felt like his model was independent of Tycho, or that maybe Tycho had borrowed it, and Tycho in his sort of paranoia felt like Ursus had stolen his idea. It was really kind of a mess. And into this mess wandered a young German mathematics teacher from Graz. He was looking for a place to land, as he was about to lose his job as a school teacher due to changes brought about by the Counter-Reformation. He had traveled to Prague, hoping to meet with Tycho and secure an assistantship. At first, things didn't go really well, but soon the older man invited the younger man to join him. Tycho assigned the new arrival a single problem to work on, as was his custom with assistants. The problem here was to come up with predictions of the motion of Mars using the Tychonic model. These were to go into what were going to be billed as the Rudolphine tables, which were sort of the equivalent to the Alphonsian and Prutenic tables for the Ptolemaic and Copernican models, respectively. As we said, Tycho had thought that better data would create better parameters and thus bring the models in line with observations. Having now come up with his own model, he was trying to do the same thing. The problem, of course, is that things aren't working out. The assistant couldn't get things to match as well as Tycho had hoped. Tycho was frustrated and impatient, and the two men quarreled. Soon, however, Tycho realized that this man was something more than just another assistant. He was brilliant. I mean, off-the-chart brilliant. For the first time since leaving Havana, and maybe even before then, Tycho realized that he had someone who might be able to really help him solve this problem. But he was also worried that the young man that he didn't know this guy really well. And he also knew that this guy had once written a defense of his enemy Ursus's ideas. And so he got really concerned that this guy was out to steal his life's works, kind of like that other student once had. On the other side, the assistant, frustrated by what he thought was a lack of data to work with, pressed Tycho for all of what Tycho had actually gathered. The assistant felt that if he could just get all the information, he could actually come up with a conclusion. But here was another source of conflict. The assistant didn't believe Tycho's model was right. He was a Copernican, and he wanted to see if the data would support that idea instead. So Tycho wasn't about to give this new man, a commoner from an obscure nowhere town in Germany, his hard-won data, only to have that guy prove another man's model. The matter hung in the balance as the two men fought and were reconciled and then fought again. The assistant prepared to leave Prague to seek his fortunes elsewhere, only to have Tycho plead with him to stay. And then came the night of the banquet, and the sober emperor, and a life cut short by the excesses of aristocratic nature. As he slowly died, Tycho realized that there was no one but this young assistant to carry on his work. His own sons, though they fancied themselves great astronomers, were probably incapable of it. He wasn't going to give his data to Ursus. There was no one else he knew and thought highly enough of, and so he called the young man to his side, and he pleaded with him to finish what he had started. He begged him to finish the Rudolphine tables. The assistant said he would need all of the data. Tycho acquiesced, just as long as he wouldn't have seemed to have lived in vain. And so it was that Johannes Kepler came into the possession of the greatest treasure trove of data in the known world, at least astronomical data anyway. Especially, though, of the planet Mars, so often observed and studied by Tycho. Kepler wouldn't end up proving Tycho right, but he would see that the Dane's name would live on forever in the annals of science as the last great naked-eye astronomer, whose observations would provide the brilliant mathematician what he needed to find the right model. As we bring this episode to a close, let me say thanks for listening. Next time, we'll delve into the biography of Tycho Brahe a little more, so that you can know more about the man and place his scientific accomplishments in the broader context of the world in which he lived. I say next time, as this week I will be celebrating my 50th birthday, and thus will likely be out of pocket over the course of the weekend when I normally record and then publish this. Furthermore, I would like to spend a bit more time doing some biographical research on both Tycho and Kepler in order to bring you some great content in the next few episodes. Between now and then, let me encourage you to go back and listen to those early episodes in the series, episodes 0 through episode 5, to refresh the observations that we've been talking about, and if your weather allows, take some time to get out on one of these great late summer evenings and look up at those beautiful evening skies. Find a large expanse of open sky and imagine yourself as Tycho Brahe arriving at the windswept island of Haven for the first time and looking up at the heavens anew with the promise of a lifetime of observing ahead of him. So until we next meet, full sails on your journey.